Hello everyone, I am Kanupriya Attrey, Assistant Professor in ECE Department of ABES Engineering College. Today we will be learning about planetary motion of movement of satellite, also known as Keplers Law of planetary motion. Now let's start with who was Kepler. Johannes Kepler was a German mathematician, astronomer and astrologer. He was a key figure in the 17th century and he provided one of the foundations for Isaac Newton's theory of universal gravitation. At that time, without resources, that was a very important that he defined the three laws of motion, starting with Keplers First Law, which says that orbit of satellite is elliptical. In nature, and Earth should lie in one of the foci. Before this, it was an illusion that satellites revolve around the Earth in a circular orbit. Means if this is Earth, then it was the illusion that they used to revolve in a circular orbit. But Kepler made it very clear that the revolution locus is an ellipse and of two foci, Earth should be placed on one of the focus. Now, giving the equation of the eclipse, it is x square upon a square plus y square upon b square is equal to 1. Now, if eccentricity is 0, then the orbit is circle. If eccentricity is 1, then the orbit is an eclipse. Now, if this is Earth and this is the locus of the satellite, the nearest point is known as perigee and the farthest point is known as apogee. So the nearest point to the Earth is known as perigee and the farthest point is known as apogee. Now, starting with moving on to Keplers second law, which says if at any time interval t1 the area swept by vector joining Earth and satellite is A1. Then again, at any time interval T1, the area swept will be same. So that means if this is the locus of the satellite and let's say here is your Earth and we join a vector from Earth to satellite, and so if this is the time interval t and if this is the time interval t, then area swept with these two vectors and area swept with these two vectors will be same. That means if this is A1 and this is A2 and this is T1 and T2, so if T1 is equal to T2, A1 has to be equal to A2. Now this concludes that in apogee area satellite moves very slow and in perigee it moves very fast. So velocity is not uniform. How we can move on to this conclusion? Say if this is T1, in the same time interval T, you leave about the area, I'm just talking about the distance covered. This is a larger distance which the satellite has covered, and in that same time span with the same area swept, this is a very smaller area which is covered. So during perigees satellite moves faster, and during apogee areas satellite moves very quicker. Moving on to Kepler's third law of motion. Kepler's third law, which says time period of a satellite, the square of time period is directly proportional to the cube of the semi-major axis. Now T is time period and A is semi-major axis. Now time period is a time taken by the satellite to complete one whole revolution, and semi-major axis is if we join apogee and perigee, so the center, if we divide it into half, so this is semi-major axis denoted by A. So T square is directly proportional to A cube, and if we take the proportionality constant, it comes out to be T square 4 pi square upon mu into A cube. Now these are Kepler's three laws of planetary motion. Now here mu is Kepler's constant. And its value is 3.986 into 10 to the power kilometer cube per second square. Now what we will be doing is, let's say if this is a Earth, this is Earth and this is the locus of a satellite. If satellite is here, then it has a force along with it towards the center of the Earth, and it has a force which is around this way. So one force is known as centripetal force and the other force is known as centrifugal force. So moving on to centripetal force, that is F in. So this would be F in. F in is due to the gravitation. So this is m, which is mass of satellite, mu, which is Kepler's constant divided by r square, where this radius is r, and mu is g me. G is gravitational constant and this is mass of Earth. Fine. So F in is m mu upon r square, let's give it a number 1. Talking about centrifugal force, which is F out. This gives you m v square upon r. This is due to the velocity of linear velocity which the satellite has. Now, if we want a satellite to be stable, to be constant, so for balance of forces, F in should be equal to F out. F out. Let's equate these two. M mu upon r square is m v square upon r. M r square r. So this comes out to be v is equal to under root mu upon r. Now this gives me the velocity of a satellite which is moving in a circular orbit. Just because the velocity is uniform, so it has to be a circular orbit. Now time period is t, which we already know. Distance covered is the circumference of the circle, which is 2 pi r, and velocity is, we have just derived, mu upon r. What we are going to do is we have to calculate t. So t is equal to distance upon velocity. Let's give it a try. 2 pi r upon mu upon r. Now squaring this time period gives you 4 pi square r square mu upon r, which gives you 4 pi square r cube upon mu. If it would have been eclipse, this would be replaced by a. So we can say that t square is directly proportional to r cube with this proportionality constant, which verifies Kepler's third law of motion. Thank you so much.